All right, so today we're doing the first law of thermodynamics, and let me start off by giving you the first law of thermodynamics. So again, so what is a thermodynamic system? A thermodynamic system is any system that has a large number of particles. Okay, and when we say large, we are talking about Avogadro's number of particles. Okay, of that order. Well, I mean, so fairly large system. Okay. Now here is the first law of thermodynamics. It states that internal energy, change in internal energy of the system is equal to the heat added to the system minus the work done by the system. So this is the first law of thermodynamics. Okay. And this entire chapter is based on that. So again, this is the change in internal energy of the system is the heat added to the system minus the work done by the system. Okay, now the sign convention is if you add heat to the system, so for this equation, if you add heat to the system, that's positive. If the system does work, if you add heat to the system, that's positive. If the system does work, that's positive. W is positive. Now, if you remove heat from the system, Q is negative, and if you do work on the system, if an external source does work on the system, W is negative. Okay, so this is the first law of thermodynamics, and the entire chapter is about this. The entire chapter is about this simple equation. Okay, we will look at various processes. Now, this law applies to all thermodynamic systems. Okay, so solids, liquids, any large particle system, this law applies to. But we will make a comment about each of these terms for ideal gas systems. Okay, so we'll look at 4 different processes for an ideal gas. We'll look at an isothermal process. Okay, isobaric process, an isochoric process or isovolumetric process, and an adiabatic process. So do any of these words mean anything to you guys? Anybody? Okay, so an isothermal process is a process where the temperature remains constant. So we'll say something about each of these terms for these 4 processes. And these are for ideal gases. Okay. We'll say something about an isobaric process. For an isobaric process, the pressure remains constant. An isovolumetric process is where the process where the volume is constant. And an adiabatic process is where you do not exchange any heat with the environment. Okay, so adiabatic process is where Q is 0. Okay, so that's the layout of the chapter. Okay, so here's the first law of thermodynamics again. Change in internal energy of the system is equal to the heat added to the system, heat added or removed from the system, minus the work done by the system. Okay, so that's the first law of thermodynamics. Okay, so let's get to the slides. Okay, so the first law of thermodynamics. Now we'll define heat first. Okay, so here is the model of a solid. So here are the atoms, and the forces between atoms can be modeled by these springs. Okay. And at any temperature, here's how a model looks. Here's how a solid looks like. Okay, so let me show you a simulation. So here is the model of ice. Okay, so here's water at 146 degree Kelvin, which is minus 130 degrees Celsius. So it's in solid form. Here is ice. And you can see that the water molecules are at a fixed location, but they're vibrating about that location. So these guys, each molecule has random kinetic energy and potential energy, because remember those, this the spring is stretched as well. At higher the temperature, longer the spring. Okay, so associated with each atom or molecule is kinetic energy because of the vibration, and potential energy because of the spring is stretched. Okay, so heat is the sum of kinetic and potential energy is internal energy. Okay, and if the molecule is excited, that's also included in internal energy, but we won't talk about that. So mostly it's kinetic and potential energy. So heat is the internal energy transferred between objects because of the temperature difference between them. So now if you bring two objects in contact, in thermal contact, and if they have a temperature difference, then heat will flow from the hotter object to the colder object. And what is being lost is that random kinetic and potential energy. So internal energy or thermal energy of the system is the random internal kinetic and potential energies. And again, rotational and vibrational energies and electronic excitations are involved as well, but again, we will keep things simple here. Of the microscopic constituents of the matter. So internal energy is the energy of all the atoms and molecules put together. Okay. Now, as practical application, so now you know what heat is. It's this internal energy of the atoms and molecules. Okay, what we are interested in is when heat is transferred from one object to another. So heat flows from a hotter object to a colder object. Now, what we are interested in is, can we get some work out of this heat? Okay, that's what we are ultimately interested in as engineers. Okay, how much of this heat can you convert to work is the question. Okay. Now, so here, now it turns out that any other form of energy, so kinetic energy, you can convert 100% to heat. The problem with heat is it's the worst form of energy. It is a form of energy. You can only convert about 20% of that to kinetic energy. Okay, that's what your car does. Well, I mean, so I'm giving you the efficiency of your car. Okay, in no process can you convert 100% of heat to kinetic energy. Okay, your car converts only about 20% of heat to kinetic energy. And what happens to the other 80%? It remains as heat. Okay, so that is, as engineers, that's one of the things we would be interested in. How much heat can we convert to work? But so we'll come to that. Okay. So in a car, heat is converted to mechanical energy. Okay. All right, now let's define some terms. We'll define thermodynamic systems. So here's a thermodynamic system, and for it to be called a thermodynamic system, the system needs to have a large number of particles. So here's a system. This is the boundary of the system. This is the surrounding. And in this system, we have a gas in a cylinder with a movable piston. All right, so this is the surrounding. So those are the terms associated with this. Let's talk about open and closed system. The system is the water and air inside, water and steam inside. And this system is open because the system particles can escape into the surroundings. Okay, so this is an open system. Here is a closed system, the system being the water and steam and air inside. And as you adding heat to the system, the number of particles are not changing. Okay. So in this system, the number of particles change. In this system, the closed system, the number of particles do not change. Okay, we will mostly deal with the closed system. Okay. Then we need to understand, you need to become familiar with these two terms, reversible and irreversible processes. Okay, so now let me go to the chalkboard here. All right, so you guys remember, let's say we'll take a, let's take a gas. So here's a gas, and we'll heat this gas. Okay, so the volume is fixed and so on. So for this gas, the volume is fixed and we're adding heat to the system. And when you add heat, the temperature will increase and the pressure will increase as well. So this process can be represented on a PV diagram like so. Okay, when you heated the gas, this was the initial state of the gas, this was the pressure of the gas, and this was the volume of the gas. Now the volume is fixed, but the pressure is rising. So the gas went from this initial pressure to that final pressure. Okay. So this process of heating the gas can be represented on the PV diagram like so. Okay. So there are all kinds of processes using an ideal gas that you can represent on a PV diagram. Okay, so let's say here's another process. And you went from this initial point to that final point. Okay. Okay. So from this initial point to that final point. Now, when you go from this initial point to that final point, if you can stop at any intermediate point and stay there and then proceed, stay there and then proceed, and come back if you wanted, then that is a reversible process. Okay, so a reversible process is if we can, each is a equilibrium point, each intermediate point is an equilibrium point, and you can go back and forth, then that's a reversible process. Okay, so, and if you cannot do that, then that's not a reversible process and that's an irreversible process. Now, again, when you're going there and going back, what you want is if you come back to the initial state, the surroundings need to be in the exact same initial state and your system needs to be in the exact same state. So here's your system and here's the surrounding. Okay. So in a reversible process, you need to be, the system needs to be able to come back to its original state and the surrounding should come back to its original state as well. All right, so that's a reversible process. And let's say this is 100 degrees Celsius and the surroundings are, and this is in contact with something that is at 10 degrees Celsius. And you know that heat will flow from the hot object to cold object. So that's a natural process. And now when heat is flowing from this object to that object, you cannot stop at any intermediate point, like I said. And also, certainly you cannot go back to the original state on its own, okay? So all natural processes are irreversible, okay? So all natural processes are irreversible. Okay. So another way to think about them is reversible processes are frictionless processes and so on. So reversible processes are ideal processes, but all natural processes are irreversible. Okay. Now, so we've defined these terms. So all natural processes are known to be irreversible. for example, free expansion of a gas, heat flowing from a hot object to a cold object, etc. Okay, so you can think of any process you want, any natural process that occurs on its own. So a river flowing down, a river is flowing downhill, and the river cannot stop at any intermediate point, and so on. Okay. The next chapter you'll learn, in all irreversible processes, there's something called entropy that increases. Okay, so all natural processes occur in a direction where the entropy is increasing, but that's for next chapter. Anyway, all right, so on a PV diagram, if you proceed along a process and each point is an equilibrium point, and if you could go back, that would be a reversible process. Well, there are no natural reversible processes, but this concept is useful in calculations, okay? So that's why we've defined it. All right, now we'll switch, we'll talk about the work done by a gas, okay? So again, remember this chapter is about the first law of thermodynamics, and the first law of thermodynamics is states that the change in internal energy of a system is the heat added to the system minus the work done by the system. So, and what we'll do is, so this law applies to all thermodynamic systems, but when we say things about each of these terms, oftentimes we'll use ideal gas systems. So we're going to work toward that. Now we'll look at the work done by a ideal gas system. Okay. So here's a gas in a cylinder. This is a movable piston. The pressure of the gas exerts a force in the upward direction. Okay, and that's the force. So this is an external force if there was any. So for instance, if you had a weight on the piston, okay, but the force that the gas exerts is in that direction. So if the gas expands a little, okay, when the gas expands, if there was a weight sitting, the gas is lifting that weight up, and the work done by the gas is the force it applied times the distance the piston moved. Now, the force that the gas is applying is the pressure times the area of the piston, the pressure of the gas times the area of the piston. And area times dr is the change in volume of the gas. Okay, so what this expression is telling you is the work done by the gas, the small amount of work done by the gas, is the pressure of the gas times the change in volume of the gas. If the volume increases, this is positive, the work done by the gas is positive. If the volume of the gas decreases, this is negative, and the work done by the gas is negative. Okay, so that's the sign convention. All right, now we talk about this because we often use gases to do work, and that's, and your car engine does that. So let me show you a simulation. Not this one, this one. Okay, so here's your car engine. Well, here's a cylinder of a car engine. Okay, and it's using this gas to do work. Okay, so we'll go over that one at a time. We'll go over that slowly. So and here's this process represented on a PV diagram like we talked about. Okay, so this is a very useful tool. And oftentimes in your coursework, you'll be analyzing PV diagrams, but these PV diagrams in the background, they have a process that goes on like this. Okay, so now here's a gas air mixture coming in. The gas air mixture is compressed and lit. Now heat was generated. This heat is what pushed down the piston, and that's where the work was done. Okay, Gary, compression, heat released, work done. Now exhaust cycle, refresh, compress, heat released, work being done, refresh, exhaust, refresh, compress, heat, work done, exhaust. Okay, so a lot of times your working substance is a gas, and so that's what. So that's why we're talking about work done by gases here. So the work done by gas is the pressure of the gas times the change in volume of the gas. Okay. So so in general, okay. So you saw that on a PV diagram, you can represent a process. Yeah. And so let's say you took a gas from here to there. You can, the work done by the gas is that area under this curve. Okay. So again, the idea is the following. The infinitesimal amount of work done by the gas was P dV. And if you integrate that, okay, and this is equal to the work done, okay, and that's P as a function of V, okay, from the initial point to the final point. And you guys all know this integral is the area under the curve, okay? Okay, so this is P as a function of V, and this integral is the area under that curve. All right, so the work done by the gas is the area under that curve. Okay, so let's say you have a gas. This is a PV diagram. You took it from here to there, and you see that was the work done. You can take the gas from that same initial point to that final point along a different path, and that was the work done. You could take it along this path, and this was the work done. Okay, so you see the work done by gas in going from an initial to a final point is path dependent. Okay, so that's an important point. And it turns out that so here's your first law of thermodynamics. Oops. Okay. So we just saw that this is path dependent. And it turns out Q is also path dependent. But their difference, this is path independent. Okay. So what we're saying is you can go from here to here. The change in internal energy is path independent. You can go from here to here along one of hundreds of paths. Okay, you can go along like that. You can go along like this, okay, and so on. Each of these terms is path dependent, but their difference is path independent. The change in internal energy is just change in internal energy, just EF minus E initial. And the energy of a system just depends on the state of the system. So this is called a state function. The energy is a state function. Okay, so that's the subtle point about that. Okay, so work done by the system and that's the work done. It's given by the area under that curve. The change in internal and okay, a system can be taken from a given initial state to a given final state, infinite number of ways. The work done and heat exchange are path dependent. The change in internal energy of the system is, however, path independent. And internal energy is a state function. Okay, so what we mean by that is internal energy is a state function. So when we say the internal energy is a state function, here's PV. The internal energy just depends on the state you are in. Okay, so E1, E2, E3. It doesn't matter how you got to that state. Okay, the history doesn't matter. The energy of the system just depends on the state of the system. Okay. All right. So now, so here the first law of thermodynamics. So the first law of thermodynamics is the change in internal energy is equal to the heat added to the system, heat added or removed from the system, minus W, the work done by the system. Okay, so in this, with the book we are using, and the convention is when you add heat to the system, Q is positive. When the system does work, W is positive. There are other books out there, some of the engineering books, that use an opposite convention. When the work done by the external sources, when work is done by an external source, that's taken to be positive. But our convention is when the system does work, work done is positive. Okay, so you have to be careful about that. So sometimes you might see this equation with a plus sign. Okay, so that's, they're just using a different convention. Okay. So the relationship between internal energy, work done, and heat transfer is expressed like that. Now, what kind of systems does this apply to? This equation apply to? It applies to thermodynamic system, any thermodynamic system. Okay, even though when we do a lot of calculations using ideal gas systems, but this equation applies to all thermodynamic systems. Okay. All right, so here's the sign convention. Q is positive when the system absorbs heat. W is positive when the system does work. Okay. And delta E is positive when internal energy of the system increases. Okay. All right, so now we'll talk about some special processes. But now is a good time to pause, and I will let you guys ask questions if you have any. Okay.